All right, so now we're going to take a look at one of the theories in chemistry and physics that really is at the foundation of pretty much everything that we do today, and that theory is called quantum theory. And you probably may have heard of this theory before, and a lot of times it's for whatever reason a little difficult to digest, but we'll try to break it down into some bite-sized pieces here. So early attempts. So early on in the 19th century, people try to figure out the structure of the atom, and the techniques that they used at the time, the laws that they followed to do their experiments. They were not very successful because the laws that they used at the time describe the behavior of objects, sort of like everyday macroscopic objects. So for lack of a better phrase, sort of like big or normal things. Okay, so for example, an apple falling from a tree onto somebody's head, maybe a car. Or do they have cars around at that time? Maybe a horse or a carriage, for example. The laws that they knew at the time of classical physics described the behavior of those types of things. What they soon realized, though, was that when it came to the realm of the really tiny, so now we're talking about subatomic particles, atoms even, so really, really tiny things, those same classical physical laws up here did not govern the behavior of these really tiny particles. So as a result, a new set of laws, a new theory, in other words, something that could describe and predict the behavior of these uh, uh, microscopic, submicroscopic, subatomic things had to be developed. And one of the earlier observations that people made at the time was that when you heat a solid, what it does is it gives off electromagnetic radiation as black body radiation, and that radiation radiates over a wide range of different wavelengths. Now, as an example of heating a solid and then that solid emitting radiation, if you think of for example, an electric stove, when you heat it up, when you turn it on, for example, it glows red hot. Okay, that's an example of black body radiation. Another example that you may be familiar with is if you want to have, or if you have one of the old school light bulbs, not the LED or anything like that, but the old one that have filaments in it. Those are usually tungsten filaments. When you turn it on, those tungsten filaments, they glow white. That's an example of black body radiation as well. So theories or laws that describe uh, macroscopic things, classical physical theory couldn't quite describe what was going on, couldn't explain what was going on in this phenomenon of black body radiation. Now, the amount of energy that was given off at a certain temperature actually depended on the wavelength of that particular form of radiation. Now, one of the limitations of classical physics was that it assumes that radiant energy was continuous, meaning that energy could be, pretty much in any amount. Okay, so it could be in any amount. So either emitted, right, given off or absorbed in any amount. However, a scientist at the time who was studying black body radiation and other types of things, his name was Max Planck, and we'll talk about Planck here in a little bit. He actually suggested that this radiant energy is only emitted or given off or absorbed in discrete quantities. You can think of those as like small packages or small bundles, as opposed to a continuous amount of energy. And he phrased those small packages, he called those small packages or bundles a quantum of energy. So that's the smallest quantity of energy that could be emitted or absorbed. Now, if you think about sort of the quantum realm, right? So it's a lot of time people hear the term quantum and they think really, really big. It's actually the exact opposite of that. It's a really, really tiny amount. And you can think of these small packages or discrete quantities as sort of like a staircase. Okay, so if you're walking down or up a set of stairs, you can place your foot right on either one step or the next step, right? So either here or you're there or you're here or you're here. You cannot be in between these steps. So what Planck suggested was that energy came in these packages. And if you can imagine, if you're going up the staircase, this is increasing energy. The energy could possess, or these quantities of energy can only possess maybe this amount of energy, or that amount of energy, or this amount of energy, or that, but you could never be in between steps in terms of the amount of energy absorbed or emitted. So this would be compared to, if you think about, instead of a staircase, right, where you have these discrete steps, you have a ramp, which is just continuous like this. Okay, but you could be anywhere along this ramp in terms of your energy. Again, increasing energy on the y-axis. So this was, if you think about it, it's fairly straightforward, fairly simple sort of idea, but it's really, really fundamental to our understanding of atoms and energy today. So what is the single quantum of energy? Well, this is defined, this packet of energy. So this is the smallest quantum or packet of energy is defined as h nu. Okay, so we've seen nu before. This is the frequency of that particular form of energy, whatever that radiation is. And now h is a new term. This is called Planck's constant, which is actually written down here. And it is 6.63 times 10 to the negative 34 joules times second, right? So this is a really small value. And if you think about it, right, small packets of energy, they're really, really tiny, they should have a small value associated with them as well. Now, all forms of energy are going to be, so energy then, whether it's a small amount or big amount, really, really large amount, energy is going to be some integer multiple of this small packet, h nu. So it'll say an integer, so a whole number multiple of h nus. You can have 5 h nus or a million or a billion, whatever. It's a small whole number of this smallest packet of energy that you have. So if you go back to the staircase example, right? So maybe possessing this amount of energy, if that's your h nu, well, going to the second step, this would be 2h nu. The third step would be 3h nu, and then 4h nu, and then 5, etc., all the way up, right? So those are the packets. They come in packets of h nu. Now, if you think about the units in this case, okay, so our energy here is equal to h, which is Planck's constant. So the units there would be joules times second. And if we multiply that now by the frequency, remember frequency has units of 1 over second, or second to the minus 1. Seconds cancel. Guess what? We end up with joules as a unit of energy, and that makes perfect sense. So that's the relationship, and we'll come back to that relationship a little bit later on. We'll do some calculations, some examples, etc. Now, one important experiment that a very famous scientist did at the time helped or used Planck's theory of the quantum theory at the time, the quantization of energy, to describe something known as a photoelectric effect. So just a quick backtrack here. When we talk about quantum of energy, okay, quantum is just singular. Okay, so this is one. packet of energy. So if we're talking about plural, more than one, we use the term quanta. Okay, that's how you that's an A, quanta of energy. More than one of these packets. This is plural here. Versus quantum, meaning one singular packet of energy. So um, Einstein used Planck's theory to explain this phenomenon known as the photoelectric effect. And what is this photoelectric effect? Well, it's actually really simple. If you shine some light, so this is our incident light here, meaning light coming in onto something. And, as we've seen before, light can exist as a wave. We have the wavelength and all this stuff. If we shine some light onto some metal surface, right? So it's coming in this particular direction. It hits the metal surface. What can happen under the right circumstances is the light can actually eject electrons from that metal. Okay, so we can say electrons can be ejected from the metal. And when that electrons are ejected, they generate some sort of charge. Obviously, electrons have a negative charge. We can amplify that and we can actually measure what that the magnitude of the charge is using a very simple meter down here. Okay, so you shine light on a metal, you can eject electrons. Now, does any light, any form of light, eject electrons? The answer to that is no. Only light, so let's go ahead. Electrons can be ejected from the metal if light is shined. Is shine the past tense of shine? Let's just say that it is shined on it. So what type of light? So light with a minimum frequency. So it has to have a certain frequency in order to eject that electron. Okay, if the frequency is lower than that minimum frequency, then no electrons are ejected. And obviously, if that minimum frequency is met or it's higher, electrons are ejected as well. That minimum frequency is called a threshold frequency for the light. What they've also found is that the number of electrons that's ejected, if that minimum frequency is met, okay, so if we'll say that we'll use the correct term, if the threshold frequency is met for the light, for the incident light, we can actually affect the number of electrons ejected. So if threshold frequency is met for the incident light, the number of electrons ejected now then becomes proportional to the intensity or the brightness of that light. Okay, so very simple experiment. You shine some light on a metal, you can eject electrons, but the light has to have a certain minimum frequency. That's the threshold frequency. Electrons get ejected. If that incident light has the minimum frequency, then we can eject more electrons if we make that light brighter. But if you have a bright light and its frequency isn't high enough, no electrons are going to be ejected in the first place. Okay, so below the threshold frequency, no electrons were ejected, no matter how intense that light actually was. So what Einstein actually proposed, based on that observation, was that the light itself, and we've talked about light being a is a wave. Okay, we saw all of the wave-like particles of light, wavelength, frequency, amplitude. We talked about diffraction, for example. What Einstein proposed was that light was actually a stream of particles. So now Einstein's saying light is made up of particles. Now, that was very groundbreaking at the time. I'll put a question mark here. Because it's very hard for people to believe because obviously, intuitively you don't think of light as being made up of particles. But according to Einstein, these particles of light were actually the things that were able to knock electrons off of that metal surface. He referred to these particles of light as photons. So a photon of light, then, a particle, sort of a little packet of light energy. So what it is, has to have a certain amount of energy, and that then he was able to bring back in Planck's equation. The energy now of a photon of light, a little packet of light energy, is now equal to h nu, Planck's constant times the frequency of that incident light. So the question then is, we talked about light being a wave. Now Einstein's saying it's a particle. Well, which is it? Is it a wave or is it a particle? And the answer is actually light is both. Okay, under some circumstances, okay, the wave-like properties or the wave properties dominate or are more apparent. And under other circumstances, obviously now the particle characteristics, the particle properties, particles dominate, okay? So what we refer to this as is the wave particle duality. And that's often very, very difficult to grasp and to accept. But when it comes to the realm of the really, really tiny, right, submicroscopic, we have to have now a different set of laws, a different theory, like quantum theory, to describe the behavior. And at that level for light, the particle characteristics come to light, no pun intended. So when we shine that light onto the metal surface, right, you can think of it as shooting a beam of particles, right? So that beam of particles, which make up the light, those beam of particles are photons at the metal atoms. If the frequency of the photons equals the energy now that binds the electrons in the metal. So you have in your metal here, there's electrons in there. Those electrons are held in that metal sample by a certain amount of energy that holds it there. If you provide enough energy to force those electrons away, right, then that light will knock the electrons loose. So we're able to overcome that binding energy. So overcome the binding energy of the electrons if the frequency of the light, the photons, which make up the light, so the frequency of the photons is large enough. Meaning now, if the energy of the photons is large enough to overcome the binding energy. You can think of it as a push and pull, right? The metals is holding on to the electrons on its surface. If the incident light provides enough energy to overcome that binding energy, then the electrons are knocked off. So what results from that then is that high frequency, and frequency in general is proportional to energy. Okay, so we can say then that as the frequency increases, the energy of the light increases as well, right? We say that those are directly proportional to each other. So one goes up, the other one goes up as well. So frequency and energy are directly proportional. Now, if we use a higher light of a higher frequency, higher energy than the binding energy of the electrons, not only do we knock the electrons off, but then we give that electron or those electrons that extra energy that was higher than the binding energy. All right. So what we can do, we can summarize that relationship in an equation. So we have here, this is the energy of the incident photon, and that is equal then to the kinetic energy of the ejected electron, that's Ke, and then we also have W here. This is called the work function. Okay, and in this case, it represents the binding energy of the electron. Okay, and that's the amount of energy that holds the electron in the metal, and we need to overcome that energy. Sometimes this work function, you'll see it often abbreviated as the Greek symbol phi, or phi, if you want to pronounce it that way, which has this symbol. Okay, so certain textbooks represent the W here in one particular way. So this is the relationship between the energy of the incident photon, the photon that or the light that we're shining on the metal. And that needs to be enough to not just overcome the binding energy, but also if it's high enough, it can also give that electron certain kinetic energy. So what we can do, we can rearrange this equation. Okay, and we can solve for the kinetic energy of the ejected electron. That is just simply equal to then h nu, the energy of the incident photon, minus the work function or the binding energy. So we can calculate, if you wanted to, the energy of the ejected electron. Okay, again, if you think about it, the idea behind what's going on, you think about a stream of light is made up of these particles or photons, packets of energy. It actually does make sense, right? And back in the day, it didn't, especially when this was first introduced, because it was sort of groundbreaking. It was opposite of what people thought. It was this whole new theory, and it is going to and has taken a while for it to be accepted by the scientific community.